It's due Wednesday. So, yeah, that's tomorrow. That's every Wednesday. So just looking at the homework real quick, it's 8 questions this time, down 3. What's the shape of a planet's orbit and where's the sun? That should be simple for you. Make sure that you explain it just a little bit. You have all of your homework assignments that you turned in are graded so you can see the feedback on, what was expected. How's the planet's speed change? That one there, I hope you got, because remember I said there's only one important thing on the second law. That's that one. 2 books, 1 1/4 kilogram and 1 kilogram are placed side by side at the same table. Is the force in the table of each book the same? This is asking another way is if Max and I are standing, are we putting the same force on the floor? And you have to have your reason why along with it. So far, not much work. Number 4 there, if you put a force on the earth and the earth puts an equal and opposite force on you, that's Newton's third law, then why is it that, when you jump up, you get pulled back down and earth doesn't come up? It's actually complicated. I will go ahead and talk just a little bit about this. One of my friends took physics at a different school when I was in college, and she just loved that her teacher said that when you pick a flower, the earth and the planets move. She thought it was just such a lovely thought. The fact is, when you put a force on the earth puts an equal opposite force on you. But how does your mass relate to the mass of the earth?
Much greater.
My mass is much, much less. The earth's mass is much, much greater. So the acceleration, according to Newton's second law, is going to be the net force divided by the mass. So the acceleration caused by me on the earth is going to be really small because of its enormous mass. Hence, it hardly moves. The acceleration caused by the earth on me, much bigger for the same force because I have a much smaller mass. In the end, they both move, but the amount that the earth moves is unmeasurable. Whereas the amount I move when I jump, well, it's kind of measurable. It's not as much as it used to be because I have a much smaller mass. So just make sure I covered that one. Now, number 5 here is the first one that's going to take a little bit of time. You have the mass of Jupiter and the distance between the Earth and Jupiter, and then you have the mass of an 18-wheeler. And it asks, what's the gravitational force of Jupiter on you? Well, first slide, Google Drive finally got up and going, so I can get the presentation here started. Enable editing, sure. Start the show, yeah. If we look here at this slide, this is where we left off, I believe, last class period. The force of gravity is capital G times mass 1 times mass 2 over r squared. I never got around to explaining this equation, right? I left off right here. So capital G is just a constant. Capital G is, if I remember right, 6.67. Boy, somebody better look it up, because I didn't look it up. It should be the front cover of your book. No, capital G. Latifah, if you just flip to the front page of the book, it should be printed capital G. What is that number? 6.67 times 10 to the minus 11 is what I remember. Is it 6.67? Okay, so I got it right. I just wanted to make sure I got the number right, rather than putting a number out there and then tomorrow saying, I was like way off. I was thinking about, something. So G is just a number. And then M, capital M as it shows here, is the mass of one object. Lowercase m is the mass of the other object. So if you're talking about this problem, let's just make capital M the mass of Jupiter and lowercase m the mass of me. Well, what's my mass? Let's make it easy. Just round your mass to 100 kilograms. Almost all of you are under 100 kilograms. I know this. I'm over. I also know that. But just round to 100 kilograms so it's an easy calculation. So you say your mass is 100 kilograms. The mass of Jupiter is what? 1.9 times 10 to the, was it 27 kilograms? It's given in the problem. And so we have those numbers. We have G, and then R is the separation. So I think, once again, the problem gives you that separation. Make sure you have all of the units in the standard units. So what's the standard unit of distance? The meter. So make sure you're in meters. And you multiply it through and you'll get a value. And it's going to be a pretty small number, which stands to reason. You don't really feel that strong effect of Jupiter. You don't notice when Jupiter's on one side of the Earth or the other side because, oh, I'm being pulled more, right? You don't feel it. So it should be a small number. But then it says, what about you in a semi? And so if we look back at that semi, I'm going to look back here so I can see the numbers. The semi has a mass of 35,000 kilograms, far, far smaller than the mass of Jupiter. But if you're standing 2 meters away from its center mass, now I should point out, if you're standing 2 meters away from the center mass, you're pretty close to the trunk. I mean, they're not 4 meters wide, that's true, but it's possible for you to be that close. So you're going to do the same calculation, but now replace the mass of Jupiter with the mass of the semi, and replace the distance from Earth to Jupiter with 2 meters. Now, if we look at the equation, obviously, if the mass is smaller, what does that do to the force? Because the force is proportional to the masses multiplied together. If the mass is smaller, what does that do to the force? Smaller. Makes it smaller. So you expect a smaller number with a semi, but if the distance is smaller, what does that do to the force? Makes it bigger. And distance is actually a bigger factor because it's squared. And so the question becomes a real question: which is having a bigger effect on you, the semi or the planet Jupiter? And so when you get your answer, whoops, let's not go there. Let's go back to the question. When you get your answer, then you'll be able to think about it and say, wow, so relative strengths, do you feel, if you walk next to a semi, do you feel it pulling you in? No, you shouldn't. Now, if the semi goes flying by you, you will be pulled in. And that's because of the Bernoulli effect. That's why they have a certain distance you're supposed to be away from the trains and the train station. Because if you're standing too close and the train is going fast, it will pull you in. Because the air is going fast and there's a lower pressure on that side. The higher pressure behind you will push you into the train. That's why you're supposed to stand back. But if the semi-stationary, it's not going to be a problem. So there's why you have that question. Now we're down to the last three. Why is it generally unnecessary to know the mass of a planet? We'll answer that one tonight. Haven't gotten to it yet, so I can't just go back to the slide. And the escape velocities, once again, those are things we'll talk about tonight. The tides, hopefully we'll get to tonight as well. So those bottom three, those are things that tonight we should get the answers for. So just want to make sure everybody remembers the homework and that's due tomorrow. It doesn't have to be done by class time, by 5 if you're turning it on paper, or by 11:55 if you're turning it online. Moving on. Centripetal force. Everybody's heard of the term centrifugal force, but what they don't know is that centrifugal force doesn't exist. Now, the word centripetal has a specific meaning. Centripetal means center seeking. In contrast to centrifugal, which means away from center. So centripetal and centrifugal are antonyms. They mean opposite things. So how many of you, when you were a kid, going on a trip at school or something, you're on the bus goes around a corner, how many of you played corners? Wow. I guess I won't use that as my demonstration there, or my explanation. In my family, riding on the bus, going to a family trip, going around a corner, we play corners, we try to crush your siblings. So we won't use...
Punch buddy.
Yeah, we didn't punch, we just crushed. Much more civil, you know. So I'll just go straight to my demonstration. So I have this, I swing it around in my head. If I were to let go, what direction would that little stopper go? Okay, it depends because it's going around a circle. So let me be a little more specific. Let's look at this picture right here. If I were to let it go right there at the top where it's shown, what direction would it go then? First, I'll start with a simple question. Will it go in a straight path or will it curve? Now, I'm not considering vertical. Obviously, it's going to come down to the ground. But horizontally, will it go in a straight path or will it curve? Straight, straight. Anybody else? Straight. Okay, you're all right. It's going to go in a straight path once you release it. Why? Because Newton's first and second laws, either one, tells you that it's only going to have an acceleration, which is a change in its velocity. Change in velocity means change in direction or change in speed, if there's a net force acting on it. Gravity's acting on it down, that's why it's going to fall down. But the horizontal direction, there's no net force on it when you let go, if we can ignore air resistance. So it'll have no acceleration, it'll travel in a straight path at a constant speed. So that's the first thing. The second thing then is what direction. So I will draw on here a few options. Option 1, straight out. Option 2, an angle like this. Option 3, like that. So I have these options, which I will now give pretty little labels. A, B, C, D, and E. Now, I should have clicker questions for this, but I don't. So I'm just asking you, which one of those paths will it follow if I let go? Okay, Max says C. Russ? C, good. Now, we being scientists, I don't tell you the answer when I can show you the answer. So what I'm going to do, so everybody be ready to duck, block, whatever. I'm going to try to let go at the instant that the string is pointing straight at that wall. Now, if the people who answered are correct, if the string is pointing at that wall, what direction is it going to fly?
Wait, you mean?
So it's going around like this. And if I let go when it's right here, what direction is it going to fly? Okay, so all it says is going toward him. So I am going to do my best to let go of it when it's right there. Indeed, I almost hit him. I wasn't aiming for you, but...
Oh, sure. Sure.
That's the way the physics plays out. That means you guys understood it correctly. It's going to travel in the direction its velocity was. I trust you. In the direction its velocity was at the instant I let go. So that's what would happen if you were like, oh, let's say you were sitting on the back of a flatbed truck and you have very little friction, like there's some loose hay on that truck and you're sitting on that loose hay. And the truck turns right. If you have very little friction, you're going to keep going in the same direction and the truck turned out from under you. So you're just going to go flying off the truck going straight down the road. If you have a little friction, of course, that little friction will pull you some in the direction the truck went before you slid off. So if you are actually going to stay on the truck, you're going to have something that pulls you in the direction that the truck turned. A force to make you turn. And so that is what the centripetal force is. It's the force that's toward the center that makes you turn. So where does centrifugal come into all of this? if you were sitting on the back of the truck, it feels to you as if, the truck bed is nice, stationary, and the ground is moving. And when this truck starts to turn, it feels like you are starting to get pulled outward from your stationary truck bed. And so we call that the centrifugal force pulling you outward from the center as you turn. But as we just talked about, there's not actually anything pulling you outward. What's trying to make you go straight?
Like the inertia, right?
The inertia. The name of it is inertia. Inertia is the name given to Newton's first law. It's the law of inertia, the law that says a thing will stay in constant motion unless a force acts on it to make it change its motion. So inertia is trying to make you go straight, not some force pulling you out. But you need a force pulling you in to keep you from going straight, and that's the centripetal force. Now, I've spent a lot of time on this because it's really important in astronomy that we understand gravity is pulling things in, like the moon. The moon is being pulled in by gravity, and that force is making it constantly change direction so it goes around the Earth. And so that force, it's the force of gravity, but we call the net force toward the center the centripetal force because it's the force that's making it turn in the circle. Question next.
Then wouldn't centripetal force kind of be the same as like the force of gravity in that situation, because the gravity is the force pulling it toward the center?
You are exactly right. Right. Centripetal force is not its own force. It's always made up of some other force. So like if you, in physics, when you draw a picture, you draw what we call a free body diagram, where you show the forces acting on an object. You never show the centripetal force because it's not a force acting on the object. It's going to be caused by one of the forces acting on the object, or maybe all of them. And so it would be the force of gravity is providing the centripetal force. Now, I've kind of covered it up, but that's okay. I can undo as long as I hit the undo button. First, it's going to undo all of my ABCs. Then it's going to undo my arrows. Okay. So the force, the centripetal force, did you have a question? Okay. The centripetal force is the result of something. In the case of this, what was causing the centripetal force when I swung around my head? What was making it turn? It was the force of the string pulling on it, which we call the tension. So in this case, it was the tension. But that centripetal force has to be Newton's second law. Sum of the forces is equal to mass times acceleration. And the acceleration to go in a circle, the acceleration centripetal, is equal to the speed squared divided by the radius. This says d because it shows in the picture d for the distance. But we often think of d meaning diameter. So I write it here, v squared over r, because r to us usually means the radius, which is what it is. So the centripetal acceleration is v squared over r. So the sum of the forces toward the center must be equal to mass times acceleration toward the center. And we call this the centripetal force. So the mass times the acceleration toward the center is what we call the centripetal force. And it has to be the mass of the object that's going in a circle times v squared over r. Now, if we look at an actual planet, it's the gravitational force that's pulling it toward the center. So the force pulling toward the center is g, mass of the object. See that plus sign? The circle with a plus in it? That means Earth. So m subscript circle with a plus, that's the mass of the Earth. The circle with a dot in it, what do you suppose that is? It's the sun. So this means mass of Earth times mass of the sun divided by the radius between them squared. Now looking at what I wrote on the previous page, Sum of the forces toward the center is mass times v squared over r. So I can write this then as sum of the forces toward the center is mass of, which object is it that we were looking at? Are we looking at the sun or the earth here? We're looking at the object that's going around. Which one is it? The earth. So that's going to be the mass of the earth. So I got to put m with the little circle with a plus sign in it for earth. Okay, that's not a very good drawing of a circle with a plus sign in it. Okay, mass of the earth times the speed squared over the radius of the orbit. So that's Newton's second law. But then looking at my picture, there's only one force acting on the earth. And that's the force of gravity, which is capital G, mass of the earth, mass of the sun, over the separation squared. Now we're one step away from answering another one of the homework questions. If I take this equation and I cancel out the things that I can on the right side, so I am going to erase the sum of the forces part so I can do canceling. Right? Otherwise, you can't. If you have equal signs, you have to. It's every term. You can't skip some. If we look at this, I have mass of the earth on both sides, so I can cancel that. I have a single radius on each side, so I can cancel those. And so I'm going to solve this and say v squared is equal to g mass of the sun over the radius. So the speed at which it's orbiting doesn't depend on the mass of the orbiting object. It only depends on the mass of the thing in the center that it's going around. And of course, its distance from the center. Now we can go a step further on this and go straight to Kepler's third law. Kepler's third law related the period with the radius. Well, if I have something going in a circle, let's simplify our math and say it's a circle at constant speed. Actually, a circle at constant speed was already a simplification we made. If it's doing a circle at constant speed, then the speed v, what did speed stand for? It's the blank divided by the blank. What is speed? What do you say, right?
Distance over time.
Distance over time. So we have something going around a circle. I know that the distance it does for one complete circle is called the circumference and has an equation of 2 pi r. And I know the time for one complete circle is called the period, which I'll use the symbol capital T for. So this is going to be the circumference, 2 pi times the radius, divided by the period. So if I plug this equation here in for that v squared, that's going to be equal to 2 pi r over the period, quantity squared, because it's speed squared. Now if I take that equation and simply solve it for period, notice I have the period squared on the bottom here, so I'm going to multiply both sides by period squared. Once again, I'm getting rid of the v here so I can do my math. It was correct having it there, but so I can do the rest of my math, I removed it. So I'm going to multiply both sides by t squared to get t on the left side. And notice I have an r on the bottom here. I'm going to actually multiply everything by r over g mass of the sun. So the period's all alone. And so what I'm left with now, canceling what I can, this cancels with this, and this cancels with that. I'm left with the equation that says period squared is equal to radius cubed times 2 pi squared over g mass of the sun. And that equation should hold true for any planet orbiting the sun. And if you look at that, you notice period squared is equal to radius cubed times a constant factor. Now, if it was orbiting something besides the sun, that constant factor would change. So we can determine the mass of the thing that's being orbited by looking at the relationship between the radius and the period. And Kepler's third law is simply this result. So remember I told you Newton's laws gave reasons for Kepler's laws. And this is showing the math for one of them. So now if we look at that homework question, we should be able to answer it. The homework question says, why is it generally unnecessary to know the mass of a planet if we want to measure the mass of the star it orbits? What information do you need to know to find the mass of the star it orbits from what we just did? Okay, he said the velocity and what else? I still didn't hear you.
The velocity of the planet is going around the star.
Okay, we need more than just the velocity. We need one other thing.
The distance.
Okay, the velocity and the distance will tell you, or the period and the time were the answers I was looking for, but velocity and distance tells you the period and time as well, because the distance is the, I said period and time, those are the same thing. The period and the radius. Those are the two things I was looking for. But velocity and distance also works because it gives you the same information. So all you need is those things. So if we're looking at an exoplanet, a planet orbiting a star other than our sun, that's what exoplanet means. We're looking at exoplanet. What the scientists try to do is determine how far from the planet or from the star the planet is and what its period of orbit is. And with those two numbers, they can determine the mass of the star that is going around. And so that's actually how you determine the masses of stars, by finding things orbiting them. So hopefully everybody can now answer that question. Can everybody answer the question? Everybody look at who's nodding yes, so you know who to ask if you have a question. Or you could always come to me. So, by the way, this equation shown right here, that's the equation that matches up with the variables that we got from Russell and Tioni, right? Actually, this has distance and speed squared. Yeah, distance and speed. So that is an acceptable set of answers. This equation here is almost exactly like what I just did. Does anybody see the one difference between what I just did and this? Now, they're using P instead of T for period. That's not a big deal. What is different? There's another mass. I did it with just one mass, and this has two masses. This actually plays back to why is the word generally in that homework question. If one mass is much, much bigger than the other, then what I did is correct. But technically, this is correct. This is always correct. But like if you take the mass of the Earth plus the mass of the Sun, you end up with the mass of the Sun. Because the mass of the Earth is negligible. It's of no account compared to the mass of the Sun. But if you have two things orbiting each other that are not that different, then you have to take the sum of the masses. So this can be used in something like, you have a binary star. A binary star is where you have two stars orbiting each other. Well, both of those stars are going to have meaningful masses when you compare them to each other. And so you have to use it this way in that case. You have to do the mass of star A plus the mass of star B is equal to 4 pi, the separation between them cubed divided by g times the period squared. And so that is a more exact equation. Oftentimes we can ignore the mass of one star, but this equation is always correct. Yes, Max?
You said that d was the distance between them, or d was the radius?
Both. Now, if you look at this, they use the symbol A in this picture. A is the separation between the two stars. You have both of them doing circles, right? If one's not a negligibly small mass compared to the other, they're both doing circles. And this number right here or right here, it's supposed to be the same thing. Just depends on who's drawing the picture and who's writing the equation, what symbols they use. It needs to be the average separation between the two through an entire period. So whatever you call it, it has to be the average separation between them for the period. So this is an improved version of Kepler's third law. It allows us to look at the orbits of any objects around each other. And notice that I did say last class period, the sun does move. The Earth's orbit around the sun makes the sun move. Jupiter's orbit around the sun makes the sun move. And those variations, Jupiter affects the Earth, so our orbit isn't constant for all time because of the other objects. And just the Earth and the sun together make the sun move a distance that's less than the radius of the sun. But it's still wobbling, so the sun is kind of going like this. Not big motion, but it's wobbling. And that's another method that's used to try to discover exoplanets. In fact, it is one of the major methods used. They look at a star, and they look for wobbles in the star. And if they see wobbles in the star, they know there's something orbiting it that's tugging on it. And looking at the period of the wobble tells you, of course, the period of the thing that's orbiting around it. And if it has convoluted wobbles, well, they can deconvolve it and determine what the different periods are for things orbiting it. And determine, there's also, you can determine the relative masses by how big the wobble is. So you can determine a lot of things about exoplanets without even seeing them because you're looking at their effects on the star. Okay. I will go back real quick. What's your question? Oh, okay. Tell me when I should move forward, sir. All right. Now we're going to talk about two cool things. The circular velocity, the speed something needs to have to go on a perfect circular orbit, and the escape velocity. So first the circular orbit. I did this calculation already. Go back 2 slides. I erased it. But I used to have up here V equals GM over R, or V squared equals GM over R. Remember, I used to have V here, and I erased it so I could do my math. Well, if I just take that equation, V squared is equal to GM over R and square root both sides, I have the speed for something doing a circle. So for something, let's say the moon doing a circular orbit around the Earth, the moon's orbit is not perfectly circular, but it's close to circular. Then we can calculate, what speed it has to do that circular orbit. It has to do with the radius. If it's farther away, if R is bigger, what's that going to do to the circular speed? But look at the equation. You're dividing by R. So if I divide by 1 compared to dividing by 100, which number is bigger, 1 over 1 or 1 over 100?
1 over 1.
1 over 1 is bigger than 1 over 100. Thank you, Tiana. So that means if the radius is bigger, it's going to have to go slower to do a circle. For the same mass of the object that's being orbited. And it doesn't matter what the mass is of the orbiting object if it's negligible. So if we look at the planets orbiting the sun, they're all fairly close to circular orbit. So we can treat them like they're circular. The speed that each one is doing, the G, of course, is always a constant. M is the mass of the sun, so it's the same for all the planets in the solar system. If we take a planet that is about, well, let's just say 10 times farther away from us, or from the sun than we are, then we're going to be dividing by 10 and square rooting. Square root of 10 is like 3 1/3 or somewhere in that ballpark. So that means that it's going to have a speed that's less than 1/3 of our orbital speed as it goes around. So the farther out planets have to be going slower for their circular orbits. Another thing that's interesting on this, most of us these days probably have a satellite dish sitting outside our home. Well, not most of us, but many of us, so we can watch Dish Network and that kind of thing. Well, back in the day, you'd have a satellite dish and you would change its position and whatnot. You guys don't remember those days, do you? They had the buds, the big ugly dishes. And people would aim at specific satellites. You can still do it. They scramble a lot of it now, but it used to be that it was all unscrambled. They assumed that nobody was looking at the satellites. And so you get this big dish and you aim at the satellites and you can watch anything you wanted. It was very cool back before they realized we need to scramble this so people can't watch our stuff without paying us money. But those satellites would move. Well, some of them would. The ones that don't move have to be in a very specific location. They have to be, first of all, over the equator. Because if they're not over the equator, they're going to be going north and south on you. But if they're over the equator, if they're doing an orbit over the equator, then you don't have to change the north and south angle. But they also have to be doing a circular orbit that takes 23 hours, 56 minutes, and was it 4 seconds to do the circle. If it's taking longer than that, it's going to move to the west. If it's taking less time, it's going to move to the east. And so it has to have just the right radius to have that right period. And so that radius is very, obviously well known and carefully calculated for what we call a geosynchronous orbit. An orbit that stays in the same position as measured from Earth at all times. And so these days with my little dish satellite, it's just pointing in one position. It never has to move because the satellite is in geosynchronous orbit. Of course, there's only one equator. You can't fill it with an infinite number of satellites. And so communications companies vie for these geosynchronous locations, and they're carefully registered, and you have to pay money to get slots in that. And so then you have interesting things like Sirius Radio. Sirius Radio, they came up with this grand idea of, okay, what we're going to do is we're just going to use 3 different satellites and have one satellite over North America at all times. And so what they have is satellites that have very eccentric orbits. When I talk about the eccentricity of an orbit, what does that mean? It is something we've learned in class. Okay, going back to the way I introduced it in class. If I said that Donald Trump is a very eccentric human being, or Hillary Clinton is a very eccentric human being, because can't show political favoritism here. What would that mean? Not part of your active vocabulary, eh?
Strange.
Given the context, you could have said crazy, but see how he's right. Strange. Eccentric means strange, odd. And so the eccentricity of an ellipse is telling us how odd it is. A perfect circle is not odd. So that's an eccentricity of 0. And an eccentricity of 1 would be going straight back and forth. So when I was showing that little applet to demonstrate Kepler's laws, it only went out to 0.7, which was fairly eccentric. Well, Sirius has made their orbits so they're very eccentric. So you have, here's the Earth, and they do orbits that are like this. Right? That's very eccentric. Now, we learned from Kepler's second law that the speed is going to vary depending on how far away it is from the Earth. When is it going to be going the fastest? When it's closest. So it's going to whip around, and the time that it's going to be on this side of the Earth over here, it's a very short time. The time it's going to be on this side will be a long time because it's going much, much slower when it's farther away. And so they have these 3 satellites, but they have these eccentric orbits so that they are in the air over North America. Actually, at all times, they have at least 2 of them in the air over North America because they spend a very little amount of time, small amount of time on the other side. So they have them so their average radius, the semi-major axis, is still the radius you need for it to be, geosynchronous, I think. I'm pretty sure that's the case. But that they spend most of their time over North America so they can constantly have coverage over North America. Now, you also might have noted that you don't need a dish pointed at the Sirius radio because it's sending a different type of radio wave. Different type means different frequency. I think it's different. I haven't actually checked the carrier frequency, so I shouldn't say that with such a surety. It's at least stronger. You can pick it up easier. So that's using the whole ideas of orbits, right? These orbital mechanics things apply to satellites. They apply to the moon. They apply to the Earth going around the sun. They apply to the sun going around the galactic center. A lot of astronomy deals with this. Now, the escape velocity. We talked about Newton's idea that, if I roll the ball slowly off the table, it just falls close to the table. Roll it faster, and it falls farther away. Well, if I rolled the ball super fast, it would go super, miles away before it hit the ground. But with the Earth curving, it could actually go too far and get away from the Earth. In that case, it's no longer orbiting. It breaks free. And using energy calculations, we can calculate how much speed it needs to have to break free of the object that it's orbiting. And so that's what the escape velocity is. The escape velocity is how fast it has to go to break free. And you notice the escape velocity is very similar to the circular velocity. It's just put a 2 inside the square root times the circular velocity. Now, that's another important thing for lots of reasons. On Earth, on the surface of the Earth, the escape velocity is 11.2 kilometers per second. What that's saying is if there was no atmosphere to slow things down, if I could project a ball at 11.2 kilometers per second, obviously very fast and undoable, that it would fly away from the Earth and never come back. But if I throw it at any speed less than that, no matter what direction, it's going to come back. If it's 11.2 kilometers per second or faster and it's not aimed at the Earth, it's going to escape. But slower than that, it can't escape no matter what direction you shoot. So that's what the escape velocity is about. So I'm safe. I can jump as high as I want. I'm never going to escape from the Earth, right? If we talk about atoms, we have atoms flying around in the air. And those atoms have a temperature. The temperature is telling us how hot they are. That was an astute statement. Yes, it's telling us how hot they are, but temperature is actually telling you how fast they're traveling. Higher temperature means that the average speed of the molecules is faster. Lower temperature means that the average speed of the molecules is slower. Hotter, move faster. Slower, move slower. Or colder, move slower. And low mass molecules travel faster than high mass molecules. So it turns out that with the Earth's mass and the radius of the surface of the Earth, at normal surface temperatures, somewhere around 20 to 30 degrees Celsius, the speed of a hydrogen atom is faster than 11.2 kilometers per second on average. So that means that the Earth actually can't hold on to hydrogen gas. Hydrogen gas escapes because it's going faster than the escape velocity. On the other hand, also helium escapes. Oxygen and nitrogen, which are much heavier than hydrogen and helium. If you look back there, you see hydrogen, the top left. It's the least massive of all elements. Now, hydrogen usually comes in a molecular form, which means you have 2 hydrogen atoms together. Helium is second. and it's 4 times the mass of hydrogen, or 2 times the mass of hydrogen gas, those two the Earth can't hold on to. You get down to nitrogen. Nitrogen is also diatomic. That means 2 atoms of nitrogen. So the mass of nitrogen is about 7 times the mass of hydrogen. And because it's 7 times more massive, it's going much more slowly, and the Earth can hold on to nitrogen gas and hold on to oxygen gas. And that's why we have air that we can breathe. It's about 79% nitrogen and about 21% oxygen. Because those are the 2 gases out there that we can hold on to. We can't hold on to the helium or the hydrogen. All because of this escape velocity equation. Now, if we go to the moon has a smaller mass than the Earth, a smaller radius than the Earth, so both those are smaller. When you play them out, it turns out that on the moon, the escape velocity is much, much lower. Because it's much, much lower, the sun heats up all gases to temperatures above the escape velocity. And so the moon can't hold on to any gas, hence no atmosphere. So it plays a huge thing about habitability with the escape velocity. Now on moon, try as you might, you're not going to be able to jump away. You could jump pretty good. You'd be measuring your height in meters rather than inches maybe, but you wouldn't be able to jump away. On the other hand, if you get to a small enough asteroid, you could escape from the asteroid. I don't know what I just did. I apparently zoomed by accident. There we go. So these are just figures illustrating what I've been talking about, calculating the circular velocity for a rocket at a radius of 2 times the Earth's radius. So I just put in the radius of, 2 times the Earth radius to get the circular velocity here at that elevation versus at the ground. Let's just go past this and get to our first clicker question. How does escape velocity compare to circular velocity? So this is asking you how those 2 equations related. I would write them down, but then you would have the answer written down. Yep. Unfortunately, I can only do a stroke, and if I try to erase that last upswing, it'll erase everything. Or while you're answering, when I finish my little lecturing thing, we'll go outside and we'll look at the sky. It may be clear enough, it may not be. Obviously, I want to go out and actually have lab where we can look at the sky because that's our goal for lab. If it's not clear, we'll come back in and I have an activity on retrograde motion for us to do. Okay, Hannah? Do you still have a register, Tiani? And Gabby?
Sorry, it's not letting me enter it.
Oh, there you go. Okay, so our answers here were 90101. Well, what does 2 1/2 mean? That means the square root. And the equations were V circle equaled square root of GM over R, and V escape was square root of 2 GM over R. So how do the 2 relate? Which one's bigger? The other one. Or, well, maybe I misheard you. That's always an option too. What did you say, Max?
I said, well, escape velocity.
Okay, you are right. I misheard him. Okay, so this is bigger because it has a factor of 2 inside the square root. So the correct answer had to have been one of these 3 because escape is bigger. It has to have 2 inside the square root, which means that was the correct answer. And that's why we have questions like this. Since no one got it right, that's why I explained it fully rather than having you discuss with someone else. How would it have helped you to discuss with someone else? No one had gotten it. So do you understand that relationship better now? Now, one more thing on this. I had the picture with the rockets that I skipped over. When NASA launches a rocket, it doesn't have escape velocity as soon as it leaves the launch pad. It goes up in speed and it continues to burn and continues to increase its speed until eventually, at some altitude, it reaches the escape velocity for that altitude, and then it's free to go. Right? So they're not going at 11.2 kilometers per second at the surface of the Earth. They're not going 11.2 kilometers per second at the time when they reach the escape velocity, because as you get farther away, escape velocity is slower. But they probably exceed it eventually anyway. Actually, one other thing about this. I don't know about you guys, but I assume that you have sat there and watched on TV the launch of a rocket. Now, see, me being a nerd, I watched all of them I could when I was college age. Unfortunately, one of them blew up. I remember that too. But when they take off, when I was in college, I always wondered, they take off and then they turn over so you see the back of it and it's going kind of sideways in the sky. It's like, why is it going sideways? They're trying to get out. It should be going straight up. Did anyone ever have that question about why is it going sideways instead of straight up? Thank you, Latifah. Well, here's why. The Earth is rotating. We don't feel the wind move. Remember, we talked about that earlier. Some of the people used that as arguments for the Earth not rotating because we don't feel the wind move. Well, that's because the air is rotating with the Earth. So when it takes off, they roll over and they travel the same direction the Earth is rotating. Why? Because then it will pick up the rotational speed that the Earth's atmosphere has. And so by rolling over on the back, they're able to actually get more speed by taking some away from the Earth, in essence. And so that allows them to get up to higher speeds with less fuel necessary.
Those thieves.
Yeah, those thieves. So each time they do that, they're slowing us down just a little bit. Not enough to make a difference, but just a little bit. All right. I've already talked about the geosynchronous orbits. Here's the actual calculation for the distance for the geosynchronous orbit. You just put in for the period 24 hours, and it just comes back to the equation I worked out a long time ago now that had the V squared is equal to GM over R. So, I was like, I checked and made sure all of these were correct. What force keeps planets orbiting the sun? That's more like it. Okay, everybody answered. We had 8 that said the force of gravity and 3 that said the force of inertia. Now, I'm not going to have you discuss again, especially because I got a lot longer than I ever anticipated I would tonight. Inertia is not a force. Remember when I talked about Aristotle and his natural motion, which has been blown out of the water? Well, inertia is the natural motion that we now understand. An object naturally travels at a constant velocity unless a force acts on it. Inertia is not a force. Inertia is the statement that it's going to go at a constant velocity unless something else acts on it. So inertia is not a force, hence the force of inertia couldn't be correct. which leaves the other 8 people the force of gravity. What is the correct thing? Gravity is pulling on them, making them change from what inertia would have had them do. Inertia, it's just inertia. It's not like I can break it down into something. It's not a force. But inertia would have had them go straight, and gravity is what makes them change direction so they stay in an orbit instead of escaping. Okay, this statement here is just conservation of energy. Conservation in science means doesn't change. So, conservation of energy is one of the basic principles that we believe to be true. Emmy Nether, she was a great mathematician. She worked out mathematically that energy has to be conserved, that you can't create or destroy energy. Now, some people might say, well, why do we talk about an energy crunch or anything like that? We can't create or destroy energy. We can't transform energy from one type to another. And so when we're talking about the energy we use, like the electricity that's lighting the lights here, what's happening is somewhere along the line, the sun's energy is being harvested. It could be direct. We can have solar panels that directly harvest the sun's energy, or it could be indirect, like we could be using hydroelectric power. Hydroelectric power is caused by the sun heating up water, making it go up into the sky, falling down into higher elevations, and then gravity making it go lower, and us capturing the energy of it going lower. Even biomass. Biomass is when we burn vegetation. Well, what gave the vegetation energy to grow? It came from the sun. Right? The whole photosynthesis process is a plant harvesting energy from the sun and using that to give energy to chemical bonds that then go on to energize the plant. Of course, even if you get to fuels, like oil, people think, well, oil has been there forever. And it's been there a very long time, but where did it come from originally? From living things that got their energy from the sun. So in the end, pretty much all of our energy comes from the sun. There is less than 1% of the Earth's total energy budget comes from something other than the sun, and that's radioactive decay. Right, so that's a small portion, but our energy is only transformed from one type of energy to another. It's not created or destroyed. And so that's what conservation of energy means. We have energy in motion that we call kinetic energy. So kinetic energy means energy of motion. And the energy of motion, 1/2 mv squared. If something goes faster, it's going to have more kinetic energy. If it goes slower, it has less. I found it very funny. I was reading a comment about collisions, and it was talking about something in sports. And somebody said, it's simple physics. Energy is mass times velocity. No, it's not. That's momentum. Energy is the kinetic energy 1/2 the mass times the speed squared. So speed is more important than mass and kinetic energy, but that energy is something that it carries. Energy is actually the ability to do work. Work, pushing on something and making it move. And so if I have a bowling ball that's flying toward me, it's going to have kinetic energy. It'll be able to do work on me. It'll hit me and make me move. That's what kinetic energy means. We also have thermal energy. That's the energy that something has because it's hot. Of course, if you get down to the nitty-gritty, I said that temperature is a measurement telling us about the average speed of the molecules. In fact, if you want to be even more precise, the temperature tells you the average kinetic energy. That's what the temperature tells you. And so when we talk about the temperature, we're giving you information about the average kinetic energy of the molecules, and we call that average kinetic energy of the molecules the thermal energy. So the thermal energy is actually kinetic energy, but it's of these little molecules that are too many of them for us to count and monitor. And so we make what we call a macroscopic measurement for the microscopic behavior. So that's another kind of energy. So the sun is hot, has a lot of thermal energy. Potential energy is energy something has for position. So once again, we have the bowling ball. If the bowling ball is sitting on the top of the table at rest, if it's at rest, it has no kinetic energy. If I just give enough kinetic energy to fall over the side, what's going to happen to its speed? I will use my stopper here. If I take the stopper and I just get over the side, what's going to happen to its speed once it goes over the side? It's going to increase. Well, if the speed increased, that means its energy in motion increased. The kinetic energy increased. What made it increase? Gravity. And so we say that it had a potential energy due to the force of gravity that made it so because it was at this position, it could convert energy from its positional energy into motion energy as it falls. So potential energy, positional. Now at this point, you're probably saying, I didn't sign up for a physics class. Well, of course you did because astronomy is physics. But this is a lot to take. We're only looking for a very superficial understanding, but you've got to have the words out there. So when I talk about the words, you have something to tie them to. I'm going to skip right past that and ask a question about these types of energy. An iron bar is removed from a furnace and placed on an anvil. What type of energy does the bar have? I think this is one where we answer all that are correct. So, no, I have them all broken down. Notice here it says gravitational potential energy. Every other place where it says gravitational, you're supposed to say, yes, that's gravitational potential energy. I'm missing two. Okay, moving on. We have 0300502. Now, this is normally a place that I would stop and have you discuss it. But because I've already been lecturing for an hour and I want to go outside and observe the stars, I'm not going to do it. The correct answer is the one that the most people said, both thermal and gravitational. Thermal because it has a temperature. Now, I have thermal energy because I'm, 98.7 degrees Fahrenheit or whatever I am, 98.6, I don't know, probably closer to 100. I'm so hot. But everything that has a temperature has thermal energy. But I said removed from a furnace just to emphasize it's hot, so it has more than you'd expect thermal energy. I place it on top of the anvil. It has gravitational potential energy because if it were to fall off of that, it would be able to convert that into kinetic energy. And when it hits the ground, it would do some work on the ground. But it does not have kinetic energy because it's not moving. Now, that's, of course, with respect to the anvil, but that's why that was the correct answer. This next one is a point that you may not know. At one time, it was thought that mass was also conserved, that you can't create or destroy mass. You'll still find textbooks, especially in high school classes, that say that mass can be created or destroyed. That's not true. If you couldn't create or destroy mass, the sun wouldn't be burning. It would just be a cold ball out there. It is constantly converting mass into kinetic energy. And so we now understand that mass is just another form of potential energy. We call it the rest energy. Is the energy associated with the mass. And so it was in 1905 when Albert Einstein proposed this, that mass is just a form of energy. And you can make more mass, take energy and make more mass. That's what they do at places like CERN, where they have a large hadron collider and they smash things together. They're making things with super high kinetic energy smashed together, and in the process converting some of that kinetic energy into mass. So they're physically making mass. Of course, most of that mass they make almost immediately then decays and gives back the energy. But that's beside the point. The whole point of having that collider is to make mass. So what's going on in the sun is this right here. You have the example here, two protons coming together. You probably know enough about chemistry that you know that we have positive charge and negative charge, and that like charges repel. So two positive charges don't want to come together. The closer they get, the stronger the force pushing them apart. And that's called electrostatic force, or electromagnetic force. Static means stationary, in this case they're moving. So you have to make them go really fast to make them come together. So the picture up above this is showing if they're not going fast enough, they will just avoid each other. But if you make them fast enough, what measurement do we use to gauge how fast things are traveling? For little itty bitty particles? Temperature. So if the temperature is high enough in the sun, for instance, then you'll have these nuclei coming so fast that they actually can hit each other. So you have to have high temperature to make this happen. But when they actually get close enough together, there are two forces that are very short-range forces that act inside the nucleus called the strong and weak nuclear forces. You get close enough, those forces become strongly attractive, and it sticks together and converts some of its kinetic energy it had, well, some of its mass energy actually, converts some of its mass energy into radiation that is heat. And so heat comes off. And so you convert some mass into heat. So the sun is constantly getting lighter as it's producing light. Yes?
That was my question.
Yeah.
It's just constantly getting lighter.
Yeah.
Does that mean that, like, theoretically over time it could affect the orbits or is the sun just so massive that it doesn't matter?
Okay. Both of your statements are exactly right. Theoretically, the sun is getting lighter. In fact, the sun is actually blowing off mass a lot faster than it's converting energy, mass into energy. So the sun is blowing off lots and lots of mass. There's lots of protons that go flying away from the sun, called the cosmic wind. So the sun is constantly losing mass, but as a proportion to its total mass, it's negligible. Even though it's a huge amount, it's losing every day. So yes, in theory, it's going to make a difference. In practice, it's negligible in difference. There's one other thing that's necessary in the sun to make it fuse, to make the hydrogens merge, and that is you have to have a high enough pressure for there to be a good chance that the particles will hit each other. You know, if I have two particles going plenty fast, but they're not aimed at each other, they just go like that. But if I have a really high pressure, that means I have lots of collisions, I have lots of things coming toward each other, so the chances of collisions is higher. Okay.